to tail, like fish, birds, and so. But some particles cannot distinguish from head to tail, like many cells are present in our body. They are elongated, but they cannot distinguish from head to tail. So they are called the apolar particles. And these polar particles, from usual, just from the ordering, like from the diagram, we can show that they can, if they are packed in very dense environment or the other conditions are favorable, they can form this kind of a state where everybody more or less oriented in one direction, such that if I calculate the mean velocity of all these heads, I will find a non-zero vector, and that is called the polar ordered state or flocking state. Also, these polar objects can align or can orient in such a fashion such that the mean velocity is zero. This is something like, it's not like exactly like antiparomagnetic, but it's like a polar apolar alignment. They can be aligned parallel or anti-parallel with equal manner, so such that it's a no zero mean velocity, but there is a ordering that can be determined by a second order quantity, which is called the nematic order parameter, and which is non-zero. And also the apolar objects can again align in a high dense environment such that they can also form the non-zero nematic order parameter Q. So this is called the polar ordered. Polar particle can form the polar ordered as well as apolar ordered state, but apolar particle can only form the apolar ordered state. In the today's talk, I'm going to focus only on the polar particle and polar order, but we have also done some work on the apolar particle and the role of disorder in the apolar species. Okay. Now, since, as I said, these systems are highly non-equilibrium, even on the individual particle level, there is a feeding of energy, and that energy is dissipated due to the collision and motion of the particle. So there is a no energy conservation, not on the macroscopic level, not on the individual particle level. So then we cannot use the usual StatMac tools or usual condensed matter tool to study this system. We cannot write the Hamiltonian for each degree of freedom. Maybe for some degrees of freedom, like for alignment, we can write the Hamiltonian. But especially for the motion of the particle, we cannot write down the Hamiltonian. For studying this system, there are various approach has been developed, and most of these approaches are dynamical, because we are understanding the system from the dynamical perspective. One of the very famous model has been introduced about 22, 23 years back by famous scientists Richek and his co-workers. And this is a purely a rule-based model. And it has been introduced in 2 dimensions, but now it has a various variants in higher dimensions also. In this model, each particle, the self-propelling units, are assumed as a point particle, but they are assumed that they have an orientation theta t at a given time. And that orientation direction is denoted by the arrows here. So suppose I'm focusing on the blue particle here. And this blue particle can move along its direction of orientation with the velocity vi, which is written here. And there is some step size here. So this is a kind of a self-propulsion mechanism. If this equation vi is not present, then the particle will not change its position. It will be only remaining to its own location with some orientation. And for orientation, particle actually look for its neighboring particles, suppose in this some small circle here, and try to get the mean orientation of all the particle inside this circle. And that is this angular bracket theta t inside this circle. And whatever the resultant is obtained from this mean, there is a small noise is added. And this small noise act like a randomness, or is analogous to the temperature present in the usual kind of a spin system. And if I get rid of this self-propulsion, then if these spins are placed, or if these particles are placed on the lattice, and then this model is very much similar to the equilibrium XY model. But one can think of this is a moving XY model. Actually, people have also developed the analog of this model on the lattice also. This is an off-lattice model, but Vicek model has been also, the analogous model has been developed on the lattice also, which is nothing but a moving XY model. And the movement is coming due to the self-propulsion or the activity of the system. So this is a very similar to the XY model, but the results are very different, and I will come to that in the next slide. And some of the pictures are shown here. So given the various strength of this noise, which is like a temperature, the larger the noise, this alignment effect will be less, and smaller the noise, the alignment effect will be more. Larger the number of particles, it means the more and more number of particles, larger the density of particle, It means more and more number of particles are interacting within this radius. It means the effect of this term is again dominating compared to this. The large density and lower noise is basically a state where the alignment is dominating, and lower density and higher noise is a state where the randomness is dominating. And this picture right here shows that this is a high noise and the lower density, which we see that there is almost a random state. And this is actually a higher density and lower noise. And we see that all the particles are more or less aligned in this vertical direction and moving in that direction. And this picture actually resembles very much like the sheep herds we have seen in the fields. So like this look like, suppose we think of these each rods as a sheep, it's like a moving sheep herds in some field or something. So this system actually shows a kind of, from here we see by tuning the density and noise, a transition from a disordered state, suppose I call a disordered state, to a kind of ordered state. And it's not only the ordered state, it's actually the long range ordered state, because it's a macroscopic ordering in the system. And there is a phase transition from disordered to an ordered state. Okay. So let's go forward. Yeah.
Yep.
Now, what are the key results? This is actually a clean model. What is the key result of these polar self-propelled particles in this clean environment? There are various results or various models, or more than actually, various studies have been done. I'm just going to focus on the key results of this system. Unlike in equilibrium, one of the interesting result of this, that this collection of self-propelled particle in d is equal to 2, where in the XY model in d is equal to 2 of the continuous symmetry system, we cannot have a long range ordered state. But this system shows a transition from disordered to a long range ordered state, which is not present in equilibrium. So this is a different from the usual equilibrium 2D continuous symmetry spin system. Second key result, and this is a picture of that, it shows there is a transition from ordered to disordered as I'm increasing the strength of the noise eta for different system sizes. And for large enough system size, actually this transition becomes first order in nature. For smaller system size, there is a continuous, but for larger system sizes, become first order in nature. Second key result of this system is that if I calculate the density fluctuation in some small subcell in the whole system, in the usual equilibrium system, if system is away from the phase transition, the density fluctuation in the small subcell, the delta n or the delta n square, the variance square, goes as is proportional to n. But in this system, this variance square, the sigma square is large, is actually is a giant, and it's a proportional to, in the actually for the nematic or apolar system, it's proportional to n square. But for polar system, it has been found that the exponent is not 1, it's not linear, but it's larger than 1, and it's 1.6. So this system has a large density fluctuation, and this is because in a given subcells, there is a more, because of this moving flock, there is a huge density variation in a given subcell because of the motion of flock in the system, and that is happening not at the transition, but in the steady state when the system is away from the transition. So these are the two key results of this system. There are various interesting other things have been studied, but these are the two key results in the clean environment in this polar self-propelled particles. Now, why we want, yes, yeah.
Madam, one question. Does the intrinsic chirality of pneumatic play any role in this kind of system?
Sorry, can you repeat your question?
Does the intrinsic chirality of pneumatics play any role in this kind of system? So,
Yeah, if I introduce the chirality, I have not introduced in this model. People have done the chiral particle also, especially in the polar particle chirality have been studied. In pneumatic, I am not very sure. So
okay.
actually it gives various different interesting phases. For very high chirality, you will not get a flocking phase. You will not get this long range ordered state.
Okay.
You will get some other spiral or those kind of structures.
Yeah. Exactly.
Yeah, there
Okay.
are
Okay.
studies on that. There are
And
studies on that.
in that case, also you need the full three-dimensional model. I think so.
Yeah, we need a full three-dimensional model. People
Right.
have studied. In recent years, people have studied that. The
Thank you.
phase diagram will be even more rich. You will get other phases. So there is another controlling parameter is the chirality. Then the self-propulsion speed, chirality, both will be like having a competition among each other.
Right. Thank you.
You will
Thank
get
you.
some other phases. Long range ordering for high chirality, you will not get.
Okay. Okay. That makes sense. Yeah.
Yeah, yeah. Okay. Okay. Now, these are some previous slide is actually on the clean or homogeneous environment. Now, in recent years, there are people have started to looking at these system in the inhomogeneous environment, and there are also some experiments also in this direction. And obviously, natural system always can have environment. Like even in any motion, we can think of there can be some obstacle present. Even in the traffic, also there can be lots of disturbance present in the moving flow. Okay, so now this is a one experimental picture of a paper in 2017. In this experiment, there is a bunch of colloidal particles. They are self-propelled because of their in the presence of some small electric field. And in this medium, there are some obstacles present, and these black dot represent the obstacles in the system. So in this study, it was observed that when the density of these obstacles is small and the color represent here, the background color represent the current in the system. If I have a very large current, like a yellow color here, it means there is like a true flocking. The particles are passing the system very easily. We can see for very small density of obstacles, there is a kind of a flocking. There is a high current, the current ranging from somewhere from 25 to 50 or so. But as the obstacle density is increased, this is a direction of increasing the density of obstacle, the black dots. Then we can see that there is a disturbance in the current, and finally, for very high obstacle density, there is almost no current. That is mostly it is black, but there is a zero current. So this obstacle has disturbed the flocking or the current in the system. But this looks also very kind of a trivial thing. But basically, people wants to study the how this this obstacle is disturbing the flocking, whether we can retain the long range ordering or not, or maybe it can give some positive mechanism in the ordering also in some sense. Okay. So this is a one experimental study, and here actually in this work, they have also studied the phase transition as a function of obstacle density from the finite current to the zero current, and they have found a kind of a first order phase transition from the flocking to the disordered state or so. But there are also some numerical simulation of like a physical obstacle placed in the path of moving rods or moving particles. And in this diagram here, it is shown this axis here shows the R is the like a blocking or the order parameter or the is a measure of the global orientation in the system. This axis represent the noise strength, the randomness, and this axis represent the increasing the obstacle density. For zero obstacle density, there is a kind of a monotonic change in the ordering from the order to the disorder by increasing noise. As the obstacle is introduced, one can see for finite obstacle, like suppose I focus on the red curve, for increasing noise, for very low noise, actually the orientation order parameter is small, but then it increases by increasing noise, and then it goes down and decreases again. And this non-monotonicity is observed for range of obstacle density. In some sense, we can say that in this system where the obstacles, and these are the quenched obstacle, they are fixed to their places. In the presence of this quenched obstacle, for lower noise, obstacles can also facilitate the flocking because there is a non-monotonicity. For very low noise, it's a smaller orientation, but for larger noise, there is a kind of increase in orientation. So that gives the idea that even the obstacles can also give a positive mechanism of ordering for certain parameters. And also there are other works where people have looked for suppose I have a well-moving flock, then how many obstacle or hindrance can disturb the flocking, and there are various work done in that direction. So this is like a one introductory slide to tell or motivate you that there are studies or there people are studying the effect of disorder or the obstacle or inhomogeneities in the polar system. And also there are work in the apolar system as well. Now, motivated with these study, we started studying simply the V-check model I introduced with the presence of the Quench disorder. So these disorders are like I have a bunch of these self-propelled particles, and then in the path of them, and this is purely a two-dimensional system. In the path of them, I place some arrows, and those direction of those arrows are fixed always, and they are fixed to their position also. And the orientation of those arrows are denoted by phi j. So this can be thought of as like there is a crowd moving in a room. And suppose I put the random arrow direction in that room and with some certain density, and crowd has to follow that direction whenever they come in close contact with that. So that orientation is denoted by phi. The self-propelled particle move along their direction with a velocity vi with a constant speed, and their delta t is 1. That is why I am not written here delta t. And the particles are going to change their orientation by looking at its a neighboring particle, aligning with their neighbors, aligning with their, if they encounter some obstacle in there or these rotators in their path or these arrows in their path with a different strength compared to their own interaction, which is mu here. And overall, whatever the mean orientation I found from these two, there is a randomness introduced here. So this is like there is a moving crowd and I place the random arrows I'm repeating. And we are looking at the effect of these random arrows on this moving crowd. Okay, I hope the model is clear to everyone.
Yeah,
Yeah,
yeah.
yeah.
Okay. Now this is simply a snapshot. Before going to details of the thing, I want to show the snapshot of the system for different density of these obstacles present or the rotators present. So this denote the number density of the rotators compared to the total density of particles. So they are, you can see they are very small in number compared to, this is like when they are in the clean environment, and this color represent the local orientation of the particles, and one color represent that the more or less particles are oriented in one direction. So we see for zero density, the particles, more or less every particle is oriented in one direction, and that direction is roughly minus pi. Now, when I've introduced the obstacles or rotators, there are some mixing of colors. It means the ordering is disturbed. Now, as I'm increasing the density even more and more, here I see there's a completely disordered scenario. There is a no like a domain kind of structure of one color or so. So there is a disturbance in ordering, and this is what the Morins and all this experimental work has also seen the same thing. Okay. Now, how it is happening and what is in detail happening in the system. For that, measuring that, we calculated the global orientation order parameter, which is defined here. I just calculate the sum of all the unit vectors of the particle orientation direction divided by the number of particle and its velocity. Actually, I calculate the velocity vectors of the particle, sum of it, divided by the number of particle and the velocity speed of the particle. And this quantity will be close to 1 if it's a perfect ordering state, and it will be close to 0 when it is a perfectly a disordered or the random state. And we measured this quantity for different system sizes, and this is a plot, and for different obstacle densities or the rotator density. And this different color denotes the different obstacle density. The black is for the zero or the clean. This is actually the V-check model, where we see as I'm increasing the system size, for even for the very large system size, I see almost a flat V. It seems for the larger system size, there is a finite ordering, and system can be thought of as a long range ordered state. Now, when I'm increasing V, there is a decrease in the ordering as a function of system size. For certain values of obstacle or the CR density of the rotators, this is the change is not very relevant. It's a very small change. But for the larger density, it's changing a lot from the smaller system size to the larger system size. We have found that if I calculate the exponent, I'm not showing those details here, the exponent of this decay, this power law decay, then the exponent, based on the exponent, if I try to do the scaling of V versus NS, for up to certain density of these obstacles, there is a good scaling collapse, and after that, we don't find the scaling collapse. And actually, the reason where we have not find the scaling collapse is actually a transition where the system is actually going from the quasi long range order to the short range order disordered state. And for the zero obstacle density is actually a fully long range ordered state. And I'm going to come into this in detail. Okay. Now, why we are saying it's a quasi long range ordered state in the presence of obstacles? For that, I just want to go back to the equilibrium XY model literature. And this slide is purely for the students, maybe for the senior person, it is well known, to just remind them. So in equilibrium system with continuous symmetry, suppose we want to calculate the 2-point spin-spin correlation function. It is a SR into S naught, average over all the reference point and many realizations. And then this is a nothing but cos of theta r minus theta 0. This is nothing but the exponential of GR, where GR is nothing but the angle fluctuation present among the particle. And suppose I look for the d is equal to 2, which is actually our dimension here. So this angle fluctuation, when this, and in the XY model, we know in d is equal to 2, there is a quasi long range ordered state. Angle fluctuation is actually logarithmic with respect to distance. And the consequence of that if I calculate the spin-spin correlation function, then it will be a power law, and the power exponent, this exponent is a function of the, in the XY model is a function of the temperature of the system and actually the spin stiffness. In this system, we have found this power is actually the function of the obstacle density for the finite obstacle density in the system. Now we want to compare this with this ours in our system in the presence of rotators of the obstacle. We calculated the angle fluctuation of different particles, the distribution of angle fluctuation. First of all, for zero obstacle density, for the for the finite obstacle density for two different system sizes. And we have found actually in our system, we are not calculating as a function of R, but this R we have replaced by the system size that will be equivalent to for studying as a function of system as a function of R. So we calculated this distribution, made this distribution for two different system sizes for finite obstacle density. And we found that as I'm increasing the system size, this curve is broadening. It means the fluctuation is increasing. How this fluctuation is increasing? For showing that we calculated the width of this distribution as a function of the system size for different obstacle density. This is only for one obstacle density. And this is a log, the y-axis is linear and the x-axis is logarithmic. And we found that for all the obstacle density, for finite obstacle density, for zero it is flat, it means there is a no change long range ordered state. But for all non-zero obstacle densities, till certain density, it is always a linear, it's a logarithmic. It means angle fluctuation is logarithmic, and it also shows a very good scaling collapse if I rescale the x and y axis appropriately. So there is a, for finite obstacle density, there is a change from long range order to the quasi long range ordering in the system. And then we further increased obstacle density, and we have found that actually there is a transition from quasi long range order to disorder. And this is a phase diagram into the noise strength versus the obstacle density space. So this lower to this red curve, there is a quasi long range order state, and above this red curve, there is a disordered state. And for zero, along this horizontal line, there is a obviously there is a transition from long range order to disordered state. But certain up to certain eta, there is a long range order state. So now we also look this system using the linearized hydrodynamic approach by writing down the equation of motion for the density and the velocity of particle, local velocity of particles, and introducing the obstacle through this quench noise in the system. And we have found that we calculated the 2-point density and the velocity correlation function, spatial velocity and the density correlation function. And when there is a no obstacle present, the zeta is 0. Then it's a usual from this linearized calculation is usual 1 by q square, which is actually a XY model result also. And in d is equal to 2, it will give the logarithmic angle correlation. But in the presence of obstacles or in the presence of this noise, we have seen that this is for the smaller q or the q tending to 0 in the thermodynamic limit. It is again 1 by q square. That actually gives that in the presence of obstacle, the linearized hydrodynamics says that there is a quasi long range order state, and in batches with the numerical results. And also there is a nonlinear study, RG calculation by Toner et al. In 2018, which also confirms that there is a quasi long range order state in the presence of the obstacle in the system. Okay. So with this, I will just give the conclusion of this part of the work in that the quench rotated disturbs flocking and make the quasi long range ordered state for the small disordered strength. Obviously, for larger disordered strength, there is a short range or disordered state. It means, in one word, one can say, if I place the random arrows in the room where the crowd is passing, and then basically one can say the crowd will not able to show the global flocking state in the presence of these arrows. So there will be no true flocking state in that system. Now there is a very good extension of this work we looked, where suppose I say that this disorder or the rotators are not quenched, but they can also reorient. It means now if the crowd passes, these arrows are fixed to their location, but their direction can reorient. So in that sense, suppose the crowd passes, they actually rotate in the direction of crowd. They also influence the crowd, but they rotate in the direction of crowd. So they are called the non-quench disorder in the system. So now we have three equations. One is the position update of the particle, which is simply the moving in the direction of its velocity. Then the orientation of particles or the self-propelled particles, they align with their neighboring particles, neighboring rotators with some stem strength mu, and there is a noise with the strength eta theta. And these rotators can also reorient. First of all, they try to remain their own orientation pi j, and they can reorient in the passing flock with a strength alpha. So in that sense, now once the crowd passes or the flock passes, they have some information of this past crowd due to this coupling strength alpha. If alpha is 0, model reduces to the previous model. If mu is 0, then model reduces to the V-check model. Okay. Now this is a cartoon picture of the result we have found, as I have shared the result here also. This non-quench rotator, in the previous slide we have seen the quench rotator actually disturbs the flocking, but the non-quench rotator actually ease the flocking, and not only ease the flocking, they also memorize the flocking. Okay, and we have shown the result here by this cartoon, and then we will come to the details of it. So suppose this vertical direction downward is my time space, and this horizontal direction is my space. This actually we are studying in 2D, but I just made this space in this one-dimensional line here. And suppose in a given spatial extent, there are the two flocks, small flocks, oriented in different direction, shown by the color blue and red. And there is a kind of a non-quench rotator. This rotating object is present, which is shown by this hexagonal shape here. And at an instant of time t1, let's say this red flock, which has a collection of SPPs inside it, interacted with this green rotator, and the interaction is happening with the strength mu. The particle is getting affected by this rotator. Particles in this red circle is getting affected by these rotators with a strength mu, and this rotator is getting affected by these SPPs with the strength alpha. And once this passes, after some time, red flock will pass from here. Green will stay to the same position. Once it passes from here, this green rotator have some information of this red past flock. So now it has a mixture of green and red. How much information? That depends on this coupling alpha. And also, the red flock now has some information of this rotator. So now that is why I marked here the green, slightly green here. Now, at time t2, because of the motion, this blue blue set of particles has come in contact with the same rotator. And then now it is interacting with this rotator. And because of this some red color here, it is, and due to the interaction, this blue subflock is having some information of this red subflock without even interacting directly with this red subflock. It got some information of this red subflock without even direct interaction with it. And obviously now the rotator have the information of both of them. So now in this system, because of this now the rotator are actually acting like a medium, which is transferring the information of two subflocks even where they have not interacted with each other. And that is the reason why in this system the flocking is eased, or it has some other details or some other information about the system. Okay, I hope the model is clear and the result, whatever I showed in this picture.
Yeah, yeah.
Okay. So now we try to understand this system again by calculating some other observable. We calculated again the global orientation order parameter as a function of noise for different densities of obstacle. So this is a kind of a blue triangle, which is a quench one, the previous model, and it shows a non-monotonicity as in some other simulations I have shown. But for finite or alpha is equal to 1 when it is the interacting with this non-quench. When it is a quench, it's non-quench rotator, alpha is finite, and finite obstacles density, this blue and red, blue circle and the red square. Then there is a monotonic change. But if I zoom in near this critical point, then one finds for the zero obstacle density, the curve is lower than this blue curve when there is a finite obstacle density, finite non-quench obstacle density. It means near the transition, there is an enhance in ordering, and also the transition shifted to the higher noise strength. It means system can persist the noise more. It can sustain the noise more. It is more robust for ordered state. And the same has been observed if I measure the V versus 1 by N or the system size. For the quench case, there is a decay in the order parameter, which shows that there is a quasi-long range ordered state. But for the finite or for the non-quench case, the ordering is enhanced compared to the for the zero density, which is the blue, which is the star here, and for the finite density non-quench, the curve is above. And same is shown by the fluctuation in the orientation, which shows that there is a true long-range ordered state in the presence of non-quench rotator. The non-quench rotator are not able to disturb the long-range ordering, but actually they facilitate or ease the ordering near the transition point. There is an enhance in ordering in the system. Not only that, they enhances the ordering, they have even more details. For looking at that, we actually look for the orientation autocorrelation of the rotators, because rotators are reorienting because of the pass flow. So we want to see whether we have some effect of pass flow in this rotator. We calculated the orientation autocorrelation of the rotator for different noise strength and for different density of rotators near the transition. So this is the one picture where I have fixed the density and tuned the noise. So for very low noise, there is a kind of some undulation, but it's almost flat. For the noise near the transition, we have seen the periodic modulation in the autocorrelation function. To understand this periodic modulation, we generated some snapshots of the whole system sample. And in the sample, here the color again represent the orientation of the particles. Circle represent the rotators, and in color inside the circle represent the orientation of rotators inside this of those particles. And this like a bright red or pinkish color represent a kind of a band in the system, actually like a large number of particles all oriented in one direction. And right now this band is actually oriented in this minus pi direction. So this band is moving in this direction, minus x direction. And this is a kind of a boundary of the one band, and this is a low density and disorder reason. And this is a very generic feature of this system, that there is a band that moves in the disorder background. Most of the particles are actually in this band. Quantity. One is that we measured the width of the band, which is basically denoted by this basically WB, which is depend on the system properties or the system parameters, width of this self-propelled particles band. Second is that we measured the width of this distribution. Suppose I fit it with the Gaussian and I measure the width of this distribution. And this width of this distribution will have a dimension of time. So this has been multiplied by some factor to make it a dimension of length. But this width of the distribution, which is a df, is a purely a property of the rotators. It's a rotator which is memorizing and having some information. And the wb, which is the width of the band, is a property of the self-moving self-propelled particle. And we can see, and we measured it for different noise strength, and we can see that they are exactly parallel to each other. In that sense, now we can see this non-quench rotators are having the information of the moving clock. And in that sense, it is useful. This mechanism or this process can be useful to get some information of the moving flock, because in general, these crowds are very high density particle. They are very large in numbers, but the rotators are very few in numbers, and tracking these rotators is much more easier compared to the tracking the particles. So we can get some information about the past flock by getting the information of the non-quench rotator. They not only facilitate the ordering, but they also have information or in a very precise manner of the past plot, and that can be utilized for some applications. Okay, shall I move forward?
Yes, sure.
Now we also try to see, I will not go in detail of these hydrodynamic equations, but we also verified these results using the hydrodynamic equations of motion. We wrote the equation for density of particle, polarization of velocity of SPPs, and also now my rotators can reorient. They also have a orientation order parameter, and the orientation order parameter for rotator, coupling of rotators to the particles is given by gamma 1. Coupling of particle in the rotator is given by the gamma 2. The gamma 1 and gamma 2 are the two couplings. We calculated the kind of order parameter in the system in the presence of these rotators of the particles. If the no obstacle present, then the result will be in the mean field analysis. The result will be simply alpha 1 by beta 1 p square. But when the obstacle is present, then we found a number here, which is a positive number and it's greater than 1. That basically shows that the order parameter is enhanced in the presence of the this non-quench rotator, which is we have seen in our numerical simulation. Even this mean field analysis is giving us that there is enhanced ordering. Also, we measured the effective diffusion constant or diffusivity of the particles in the presence of obstacles, and the speed of the particle or the convection speed of the particle. So this X represents the convection speed of particle, and the gamma 1 is the coupling, and again alpha 1 prime minus A prime is a positive number. And we have seen when there is a no gamma 1, is a normalized speed is 1, but in the presence of gamma 1 or in the presence of the coupling to the non-quench rotator, there is an increase in the convection speed, and that is basically responsible for the more ordering in the system, because more the convection or more the speed of the particle, there will be faster the ordering in the system. And diffusivity is also, so diffusivity is decreased in the system. So this is the plot of the diffusivity for the as a function of obstacle density, which is decreasing as a function of obstacle density, and this is the plot of the convective speed, which is actually increasing as a function of the obstacle density. Even in this linearized calculation, we can get the information of the system, what is happening in the pure nonlinear, full nonlinear analysis of the numerical simulation. With this, I will conclude this part of my talk. This non-quench rotator enhances the can be utilized for the crowd control and getting the information. Above two work is actually for the extrinsic inhomogeneities, where there is the inhomogeneities present in the medium. Now I will show one result for the intrinsic inhomogeneities. How much time I have, roughly?
You can safely take 10 more minutes.
Okay, fine. I'll finish in that. So now I will show one study where we have studied the intrinsic inhomogeneities, and that is also relevant and useful, and that is also naturally present. So the intrinsic inhomogeneities can be of various kinds, like each particle can be of different types. They can be having a different self-propulsion speed. They can experience different thermal noise. Not necessarily they are experiencing the same random environment, because as I said, the delta theta is a temperature analog, but it's not a temperature. There's no thermal bath in the system. They can experience different randomness. Also, the particle can be moody in nature. Not every sheep in the herd to be aligned number or following its whatever is the person is suffered is raising it. So they can be in moody, some may be aligning more, some may be aligning less, some may not be aligning at all. They can be different in size, they can be having a different interaction radius, not necessarily everybody is interacting in the same number of neighbors or something. But there can be different kind of a scenario, but this is coming through the particle properties. They are not coming through the background or through the medium. And that is why I'm calling it the intrinsic inhomogeneity. And they are also very much naturally present. Only one difference is now in the intrinsic inhomogeneities, doing the analytics become little difficult. It's not like impossible, but it's become little difficult because the inhomogeneity is present now on the particle level, not on the spatial level. So I cannot introduce in the spatial equations or the temporal equation the inhomogeneity. It has to be introduced in the each particle level. That slightly different approach has to be used. Okay. So now with this slide, I will show one experimental paper. Or this is this intrinsic inhomogeneities, whatever I mentioned, is not only like some like just approximation. It is also present in natural system. Actually, it can be present for all kind of different examples I have given. But I'm just showing for one case where in some bacterial system, the speed distribution of particle is calculated. And it's actually, if it is a constant speed, it should have a one delta function kind of a thing. But we can see for two different kind of species here or the particles, there is a very broad distribution is found. For one case, it's like a almost a very broad kind of a log normal distribution. For other case, it's a kind of a little bit narrow distribution here. The speed inhomogeneity is present in the system. It can be quench or non-quench, but for our system right now, we have assumed the quench speed. But even in the real system, it can be non-quench and it can depend on the environment and the background or the neighboring particle. We have also done some work on that, but we are not focusing on that right now. We are only focusing on the quench speed, where each particle have a different speed and their intrinsic different speed. They cannot move more than that. They have a different speed of their motion. Okay. So now with this, we would like to model the speed inhomogeneity in the system. The model is similar to the previous model. Now, only difference is that each particle have an index I in their speed, and this gives a different speed for different particle. And the speed distribution is obtained from the Gaussian distribution shown here. Is written here. Yes, mu is the mean of that speed distribution, which you can call it like the mean speed in the system. And sigma is the variance in the speed distribution. If sigma is 0, then it's a Vcheck kind of a model. And then we tuned the sigma and studied the system. And the second equation is the alignment mechanism, slightly different. It's actually the vector alignment, not the angular at the previous case. So this is the alignment with the neighbors. And then this is the randomness present due to the noise. And we simulated this system for various sigma in the system. And obviously for system in the we can study for different noise strength, but we focus on study actually in the ordered state, not near to the phase transition. Okay, so now we have plotted the global order parameter for a fixed noise for different sigma as a function of 1 by n. So these are the plot as a function of 1 by n. There is a black also which is hidden behind the red. Black, red, and blue is for different increasing sigma. Black is for 0 sigma and blue is the largest sigma. And we can see for all cases, there is a perfect long range ordering state. There is no change in order parameter. Angle fluctuation is almost, there is no wideness, their width is not increasing. It's a perfectly long range ordered state. But one difference we found, when we look for the time series of order parameter, this is obtained in the steady state. But suppose I look at how the system is evolving from the disordered state, then the black is for the 0 sigma, 0 variance in speed, and the brown is for the largest variance we have looked. Then for the 0 variance, actually system takes large, for a same system parameter, system take larger time to reach to the ordered state compared to for the finite sigma, where the system actually ordered very fast, and this order is really very different. It's this much. The brown is ordering roughly at 2000, and this black is ordering roughly at 12,000 or more than that. There is a difference in the order and time it takes, or maybe ordering kinetics. I should not use the ordering kinetics because we have not measured the length scale and all, but there is a difference in the time scale of ordering in the system. Okay, that actually motivated to understand this system in detail. So we looked at what is happening Till now, we have only showed in the orientation ordered space, but what is happening in the density space in the system? For that, we calculated the local density of particle in the sample for different sigma. So this is for the clean case, and this is for the maximum randomness or maximum inhomogeneity. And we see, and the pink color represent a really very high density cluster. So for 0 sigma, there are very bunch of particle with very high density cluster. For larger sigma, we have seen more or less a homogeneous flock. There is a not very dense cluster. And these particles are all moving in one direction because we have seen there is a long range order state. The long range ordering is present here also, but the flock or the density has become more homogeneous for larger sigma. We measured the density fluctuation in the system as a function of sigma, and we have seen in support to this figure that the density fluctuation is decreasing as I'm increasing sigma. The system is becoming more homogeneous by increasing the sigma or the speed in homogeneity in the system. What is the consequence of this in the system and why it is leading to the faster ordering in the system? To understand that, we actually perform a kind of a small experiment in the simulation. What we did is, uh, in the whole sample, we randomly place some particles in some fixed direction. So suppose I have some 10,000 particle in my system. We place at 2 or 3 places some particles with a direction in the plus x direction, like in this direction of this arrow, and they are randomly placed at some location. Only 3 to 4 particles, not more than that. Their density is almost very small. And we want to see the response of my system, the self-propelled particles, to that direction, because those particles will be acting like external field, because they have a fixed direction of motion, fixed direction of orientation. They are not moving. I want to see the response of my system to that orientation direction. So this picture bottom shows the sigma 0. There is no speed in homogeneity. And as I'm going up, there is an increase in the inhomogeneity. And the color of these arrows shows the black. I started my experiment, let's say at t is equal to 0, this test at t equal to 0. And in this picture, the red shows all the particles which were present in this small circle of interaction radius of the given blue particle, cyan particle here, at time t equal to 0. The red means they were all present at t equal to 0. But with time, these particles are going to pass this from the circle and some new particles are going to come. If they are going to pass and replaced by other particles, that is denoted by the black color arrows here. If we see with time, these particles, the red particles are replaced by the black, and slowly the flock is orienting towards this positive x direction in the direction of this arrow. The system is responding to the external perturbation, and this response is happening by replacing the neighbor particle in its surrounding, because once the neighbor particle passes, they actually give this information to the other particles, and slowly the whole system will order in that direction. But this full response, almost when the 99% or maybe 90% of the particle is the new particle, not the old one, takes some time step of roughly 10,000 in our simulation. But when I did it for the larger sigma or for the finite sigma, then we see this response is happening quicker. It's just from the 4,000 step for sigma 0.001 and in just 700 step for the sigma 0.01. Although the number of particle is also in the cell is very small because flock is now more homogeneous. So for looking at it, first of all, system is responding faster. If I measure the response function or something, it will be quick. But what we measured, we wanted to say in terms of in the update in the neighbor list, we measured the neighbor list of the particles, and we measured how fast the system is updating its neighbor, how long it can remember its neighbor. That I'm calling the neighbor autocorrelation function. And this is a plot of the neighbor autocorrelation calculated from this time series of the neighbors. So for black, there is a sigma 0, and the blue is the largest sigma. And we see the neighbor autocorrelation is, first of all, exponentially decaying with time. That is fine. But for 0 sigma, it is having a large tail. It means it remembered its neighbor for a very long time. But for the finite sigma or for larger sigma, it is decaying faster. And on this autocorrelation time is decreasing with sigma in the linear fashion. So this faster update of neighbor is actually leads to the the quicker or the faster information transfer in the system, and that promotes the enhanced ordering in the system. With this, I would like to conclude about this, that the intrinsic speed in homogeneity promotes information transfer by faster update of their neighbor list, which is not present for sigma is equal to 0. So this inhomogeneities again act in the positive sense, and it promotes the ordering in the system. I'll skip this part of the talk. This is again about the bond disorder. And I will come to the conclusion. So now we have seen the three problems here. Two is about the extrinsic inhomogeneity and one is the intrinsic inhomogeneity, both having the positive and negative feedback. Okay, intrinsic, I have not shown the negative feedback, but it can also have a negative feedback. The quaint random disorder disturb flocking in 2 dimension. Non-quench disorder ease flocking and store the information of the moving flock. Intrinsic speed inhomogeneity accelerates the information transfer in the system. We can also see some other kind of, we can have a look for the system in other perspective. We can see for other kind of a disorder, how disorder can influence the ordering kinetic in the system. We have only looked for the steady state till now. What happens if most of the disorder I introduce, at least the extrinsic one in the orientation field? What happens if I put the disorder in the density field? What is the role of disorder in higher dimensions and the disorder in the wet system? These study are for the dry active system. There is a no fluid background. So there can be other hydrodynamic interaction in the wet system. And obviously, we are looking for some experiments to cross-verify these results. And with this, I would like to thank you for your kind attention and questions.
Yeah, thank you, Dr. Mishra, for a wonderful talk. It was a great exposure to to a very exciting field of soft matter physics. A fantastic talk. So I can see two questions in chat box, Shraddha. You can read it yourself, or I can read it for you.
I can also read maybe.
Yeah. I think there is one question from Muktish at 11:04 a.m.
Yeah, 11:04 a.m. Okay.
Yeah, the
The
second one.
non-lattice model, Recheck model maps into XY model in the V tending to 0. Can one expect the behavior of paramagnetic if the Recheck model is described on lattice? Can one expect the behavior of
Behavior of ferromagnetic clock model.
Yes, clock means
actually, yeah.
discrete model. In the XY model is a continuous SO2 symmetric model, but
Yeah.
clock model is a discrete symmetric model. So suppose you have you choose 6 different angles out of 2 pi,
It's like a
something
clock
like that.
model, I would say.
Yes. So if you discrete, if you put this VSEC model on the lattice, so can one expect this behavior of the ferromagnetic clock model?
Yeah,
Since the
actually, people have looked on the. Actually, they have called it like a moving pots model. People have looked. There is a flocking, and although there is a band formation also.
Mhm.
There are study, and then not only in the clock model, people have also looked the. This is called the active icing model, where the spins are like icing. They can only move in either a forward, backward, or up and down only. But the space is 2 dimension.
Huh.
Alignment can happen in any direction. The interaction can happen in any direction. Even in that system, people have seen there is a long range out.
Okay, and I think in VSEC model you have observed the formation of the vortex, the flocking before going to the ordered
Yeah. There
phase.
is a formation
You
of vortex. Yeah, I
vortex.
have seen your video also. It was
Yes,
very nice.
and even in the clock model, I can give you the reference that was studied by Yamamoto and Ono, a Japanese group. They have published a result in 1990 that even in discrete clock model, they have observed the Kosterlitz-Thouless kind of phase transition.
In the equilibrium.
In equilibrium, yes.
Yeah. Okay, that's nice. I would like to see. Actually, we are planning to, right now, we are focusing on that. We are doing some study. We are looking in this kind of a clock model. I am calling it the POTS model. It's like a 4 directions only.
Yeah.
And we are trying to look for this different kind of defects present, plus minus one kind of a defects, whether we can see in these systems or not. Yeah. So that can be found. Yeah.
Yeah.
So it's interesting to look at.
Yes. And thank you very much for a wonderful presentation
Okay,
of your.
thank you very much, Muktish. Yeah.
Okay.
Yeah. Okay, Dr. Mishra, there is another question at 11:11 a.m.
Yeah,
by
that has been by
Sujan there. Yeah,
Sujan.
yeah,
We can see from the steady state snapshot that the orientation of SPPs are disordered as we go to the right. Is this disorder completely random? Can we get back to the initial state somehow? Which picture, Sujan, you are saying in which slide? Sujan, are you around? Sujan? Uh, from the steady state snapshot, the orientation of SPP are disordered when we go to the right. Disorder completely random. Can we get back to the initial state somehow? No, actually, if we start from the disordered state, we can go to the get back to the initial state. So in the picture, if I remember correctly, in the picture I have shown the right direction was actually the increasing the disordered strength. Obviously, for larger disorder, I will have a completely random state. So you are saying, suppose
I guess that is from the initial part of the talk, probably.
That is from the initial part of the talk. Okay, let me just go to my slide. Yeah. Sorry. You just stop me when I'm on that. This one?
Yes, probably, because these are the steady state snapshots, right? And the
Yeah.
question indicates about the steady state snapshot.
Yeah, this is in the steady state. Yeah. Yeah. So I started with a random state. This one is not able to order, but this one is able to order. This one is able to order to some extent, but there are fluctuations. Your question is, can I go back to the initial state? That is the question.
I think he meant that actually it's possible to get back to initial state again.
You can go, well, for that you need to change the system parameters to get back to the random state again. In this, for the current, we started with like we quenched the system. We started with a random state. We are not looking for the ordering, but we are looking the steady state in a given system parameter where the system is finally will be in the ordered state.
Yeah. Okay. I think there is a last question from Souvik Chatterjee, the last one.
Let me just
What is
see.
the physical significance?
What is the physical theory plots of the inhomogeneous speed promotes faster information transfer? Can we deduce any relation between T and sigma? What is T? Sigma I can see. Okay, T is the time this takes it to reach to the steady state. Souvik? I have only said one time, which is this
Actually,
autocorrelation.
that is from the last plot when T
You
and
are correct.
sigmas are plotted in a circular manner.
You can get that. Let me come to that slide. You can get that. Actually, I have not shown in this talk, but we have found a very robust exponent, although I don't know the answer to that exponent. This delta phi versus sigma varies decay with the same power law. Okay, this is also a power law. I said the linear. This is a sigma versus T. This also has the same power law. We have measured some other angle correlation also. That also have the same power, which is close to 0.2. I don't know the answer to this. Why it is a 0.2 or it's a 0.25. No, it's not 0.2. Sorry, it's a 0.4. We have found the same exponent everywhere.
I think that can be some exponential relation, right? Because we can clearly see that if sigma is increased very slightly, the disorder actually decreases, and that is very rapid with the change. We can see that at t equals to 4000 and sigma equals to around 0, it is completely disordered, whereas for sigma equals to 0.01, we can see that the disorder is much more minimalized. So can we say that there is some nonlinear relation between sigma and t as we increase sigma? Like
There
that?
can be, but we have not looked in that one, I'm saying. There can be. There can be. We have not looked the problem in that way. Yeah, there can be. Obviously, there will be some relation between T and sigma. Yeah.
Yes, and unless you plot in logarithmic scale, you will not be able to conclude that it is exponential.
Yeah, it's exponential order. Yeah, actually, one can do that. We can do, but we have not looked at that problem in that perspective yet. Yeah, one can do that and have some relation if there is some relation. Actually, one can actually measure this time. This is a better one. we can just look at the time it reaches to steady state as a function of sigma, and this will be a direct measure of that.
Hmm.
Yeah.
Right.
So, yeah. Okay. Yeah. Any more questions?
I don't see any other question. So if not, let us thank Asif.
Yeah. I have a very naive question.
Yeah,
So,
please.
in a real life flock, you see that the radius of curvature of each entity is sometimes equal. So the R is very much fixed. But in VSEC model, we see that the radius of curvature is different. It's larger for the rightist one or the last one, and as you go towards the another direction, it decreases sometimes. So how to incorporate that real life modeling in the VSEC? Is there any modification of VSEC model which very much match with the real life flock of bird or
There
something
are
like that?
various variation of VCheck model. Even this radius of, first of all, in VCheck model, it's not directly we are putting radius of curvature. It's a result of the system, whatever we are getting. Yeah, obviously we are not getting this curvature. In VCheck, we are having a almost flat flock. It's like a straight line kind of a streaming kind of a system. So for if looking for the radius of curvature, actually there are some studies or some modeling has been introduced where actually people have introduced the other interaction in the flocking. There are like some kind of other traction or different kind of interaction term. And then people have seen that there is a curvature kind of structure has also formed. But in which, yeah, there are various variation have been studied. Yeah.
One more most important variation is suppose you are considering here in the VSEC model within a circle. So actually the modification was done within a solid angle which is not a circle.
Yeah, that is
Within
also
circle.
done in the
So
solid
that
angle.
was
Yeah. As a
recently
function of solid angle, the
published.
phase transition is studied. Yeah,
Yes, it
that
is
is.
Right.
recently published.
Yeah,
Right.
yeah.
Some people also talk about some kind of new variable. Uh, it's called spin of the classical spin, equivalent spin, similar to quantum spin, and they try to understand how this spin evolve with time whenever there is a wall or any obstacle. So
Yeah, yeah.
yeah.
And another important modification is the role of viscosity.
Yes.
So if so that was not done in VSEC model. So
Yeah.
you just include the viscous effect. Okay.
Yeah. Include the viscous effect, we include the inertia effect. There are various
Yes, yes.
things.
So that was
Various
also published in 2019. It was a PRL paper. So to
yeah.
study the schooling of fish, so they introduced the effect of viscosity of water and
Yes.
got the different result.
Yes. Yeah.
Thank you, both of you.
Thank you.
Okay. Thank you. Thank you very much, everyone.
Okay, thank you, Dr. Mishra. It was a most exciting session indeed, this plenary talk session. So with this, I conclude the plenary talk session and immediately hand over the session to the convener Shovik, who will be conducting the next oral presentation session. There will be two talks, but now Shovik, I hand over the session to you to announce things. Okay, thanks everybody for joining, and please stay tuned for the rest of the session.
Okay, thank you, Dr. Mishra, for the interesting talk, and also thank you, AC sir, for taking the charge. So now we are at the beginning of our oral presentation session, where we have two presentations actually. And for this session, I would like to hand over the mic to Poulumi to take charge of this session. And thank you all. Please stay tuned for the rest of the conference. Thank you.
Thank you, Shobit. Good morning, everyone. Welcome to the oral presentation session of this conference. Today we have total 4 presentation, 2 in this session and the other 2
Okay,
in the
sorry,
upcoming.
just an interruption. Dr. Mishra, you can stop your screen sharing now.
Yes, you can stop sharing.
Yeah, thank you. Poulumi, please continue.
Yes. So just a gentle reminder to the speakers, you have 15 minutes for your presentation and another 5 minutes for the question answer session. Now I would like to request all of the participants to please turn off your camera so to save some bandwidth, and also please keep yourself muted. So without further delaying, I would like to welcome our first speaker, Mr. Shubhajyoti Bid from Indian Institute of Technology, Delhi, to deliver his presentation. You can start your presentation now.
Okay, hello. Good morning, everyone. Can you listen to me?
Yeah, you are audible.
Okay, great. Any internet issues?
I guess no, you can start your
Yeah,
presentation.
I can see, I can hear.
Is the screen visible?
Yes, yes, screen is visible.
Okay, great.
Yes, your
Are the
slides are
slides
visible,
visible?
perfectly visible. You can start now.
Okay. So good morning, everyone. First of all, thank you for the opportunity for giving me time to present my MSc project. This is basically my MSc project. I am going to discuss about an extended version of the famous SSH model, which I named it extended 4-bond SSH model. This was my MSc project, and I have published a paper out of it. So I'm going to explain that what is there in that paper. So the outline of the talk is like this. It goes like this. I kept some of the very basic slides of topology, which is very mandatory slides, which are kept in everyone's talk in the first section, and the second section goes as I will introduce the famous SSH model and how basically it's a very simple model of topological insulator. So I will go like this. I will first discuss about the band structure of SSH. Then I will go to the main flavor of the problem, that is where the topology of the problem lies. And at last, there is another most important thing, physically most important thing is the bulk boundary correspondence and the edge states. The third section of the talk is introduction to SSH4 model and the differences with SSH. This is where my work lies. Here also I will go like that, band structure of SSH4. Then this two is very important, that is motivation of the research, why I took this model and why I spent 1 year or 1.5 years of my masters in doing this project. In the motivation of the research, the two or three questions will be arised, and in order to answer that 2 3 questions, I need to introduce what is decimation scheme or renormalization scheme to answer that question, and then again I will go with the flow, that is find the topological phase transition using Wilson loop, and ultimately I will come to the bulk boundary correspondence and edge state again for the SH4 model. So first let's come to the topology. That is, what is topology? Topology has nothing to do with physics. It has in earlier days it was just a part of abstract mathematics, where topology basically is a branch of abstract mathematics that deals with global geometry of the system, and it states that the local changes in geometry does not affect the global geometry of the system. In very easy manner, it basically deals with number of holes in the system. For example, a sphere has no holes, a donut has one hole, this has two holes, and it has three holes. This number of holes is called the genus, that is, genus is 0 here, genus is 1 here, 2 here, and 3 here. So whatever I tell till now, everything is captured into this formula called the Gauss-Bonnet theorem. It states that if we integrate something called the Gaussian curvature, this kappa, throughout the whole area of the object, the closed surface area of the object, and divide it by 4 pi, we always get an integer value which is called 1 minus g, that is 1 minus genus, where genus is number of holes of the system. So if I do it for a sphere, this answer will be 1, so that G is 0. A sphere has no holes in it. These slides are very important because there is something called winding number in physics, which is exactly similar looking formula like this, where this Gaussian curvature is played by something called A, which is this quantity. These K's are the eigenvectors of the Hamiltonian of the model that I will discuss. And this is called Berry's curvature, and this is called Gaussian curvature. This formula looks similar, and this also gives us an integer value. It gives us the winding number of the system. This is valid for topological insulators. That's why these are called topological insulators, because they follow these kind of formulas. Okay, so let's discuss about the basic and the very famous SSH model. The SSH model was previously used to model polyacetylene. It was a dimer model, and it can give us a metal insulator phase transition. That was there previously. now topology is being associated with this model, and how it's done, I will tell that. So this polyacetylene have double bond, single bond repeated alternatively in space, so that it is modeled such a way that two hopping integrals are repeated alternatively in space, that is TATB, TATB, TATB. The unit cell of this model have two atoms, so the Hamiltonian will be 2 cross 2. First, I will go through the analysis of band structure. For analyzing the band structure, what I need is to write the tight binding Hamiltonian first in real space, which looks like this. Then I need to Fourier transform it to K space, which looks like this. And then I need to diagonalize this Hamiltonian either by Mathematica or by hand, whatever anyone wish, to get this dispersion relation. And I plot this dispersion relation for three different parameter regions. One is TA equal to TB, where the system is metallic, that is, there is no gap at the blue ozone boundary, and TA greater than TB and TA less than TB. Here the system is gap, the system is insulating, there is a gap in below ozone boundary. But these two phases, that is TA greater than TB and TA less than TB, that is one hopping is greater or less than other, gives us same eigenvalues, so the band diagram looks same. But the question is whether these two phases are actually same or not. This will be captured in topological aspects of SSH, where we now need to look at the eigenvectors of the system. That's why there was a K in that winding number formula. That way we need to look at the eigenvectors of the system in order to calculate the topological invariant. These are TKN, Tholas, Kohomoto, Nightingale, these kind of invariants are these. So in order to do that, I find the eigenvector of the system. The eigenvector of the system looks like this. And if I directly put this K in that winding number formula, in principle, I should get some winding number, or whether 1 or 2 or 0, I will get winding number. But in order to visualize the winding number, I need to write the Hamiltonian like this. I need to decompose this as a Dirac kind of Hamiltonian, that is D dot sigma or H dot sigma, whatever we call it. And then we get Hx, Hy, and Hz is 0. And these are the two components of that D or H vector, whatever we call. And if I plot this for that three parameter regions, what I get is this. If TA is equal to TB, then it's basically a circle in this H plane, and this circle touches the origin if TA is equal to TB, that is the metallic condition. And the two insulating condition which were there, TA greater than TB and TA less than TB, that is one hopping is greater or less than the other, looks like this. These now, that two phases, that the eigenvalues and the band diagram are looking completely same, they are not same. They are different, because in one phase the circle encircles the origin, so this should have a winding number of 1, it winds the origin, and this condition does not wind the origin. So now if I put that eigenvector in that formula, what I get is the mathematical quantification of these two plots. That is, in one case the winding number becomes 1, and in other case the winding number becomes 0. That is, these two conditions are satisfied. So basically this this circle is has a topology of a circle. It has no holes in it. It does not winds anything. And this you can think of as a topology of a donut, because it has a hole inside it, that is the origin, and it winds the origin. So it has a winding number of 1, that is number of holes equal to 1. We can compare it like that. So, and another most important thing is called the bulk boundary correspondence and the H states. These are very much important experimentally also. And I will dictate this bulk boundary correspondence. That is, the bulk of the topological insulator speaks with the boundary via bulk boundary correspondence, which states that H states appears in the boundary of topological insulators if a Zach phase can be associated with the bulk and vice versa. So that if I have H state, without doing any calculation, I can tell that the bulk have a winding number of 1 or a Chern number of 1 in dimension, whatever it is called. And if there is no H state, that means that the bulk have winding number 0. That is, it is in topologically trivial phase, there are no H state, and in topological non-trivial phase, there are H states. Now, now in order to look at the H state, we need to apply something called OBC. Construct the edges of the systems, and we need to make the lattice finite. That is called open boundary condition. So I have plotted these two H state for the SSH Hamiltonian for n equal to 30. that is 30 system size. I have plotted this to 8 state, and it clearly says this. Clearly, you will look at it and say that yes, the bulk is very much insulating because the wave function decays exponentially inside the bulk, and the wave function remains at the edges of the chain. Now let's come to the model that I have worked on, that is SSH4 model and differences with SSH. So SSH was a simple model. That's why it is very famous, because of its simplicity, and it can capture all the flavors of topological phase transition, the symmetries related to everything. What symmetries are there, inversion or chiral or time reversal, everything this SSH encaptures. So that's why it is so famous, and it's because of its simplicity also. But SSH4 is not that simple. You can look at it that this SSH4 looks like this. Instead of 2 hopping integrals, 4 hopping integrals are repeated: A, B, C, D, A, B, C, D, A, B, C, D, and it goes like this. So now the unit cell have 4 atoms. So the Hamiltonian will be 4 cross 4, and everything will be difficult in this situation. So first, let's go like this. Let's first calculate the band structure of SSH4. The band structure of SSH, in order to calculate the band structure of SSH4, I go on with that same process. I write the tight binding Hamiltonian in real space. Then I do the Fourier transform to write the tight binding Hamiltonian in K space. And to compare it, I kept this SSH Hamiltonian. This looks like this 2 cross 2 simple, but this is 4 cross 4. And if I diagonalize this, it will have a e to the power 4, so that 4 bands arises ultimately. And the dispersion relation looks nasty. It looks like this, and whereas the SSH dispersion looked like this, it was very simple. Now, if I plot this dispersion relation simply for 4 values of TA, TB, TC, TD, it somewhat looks like this. That is, I kept it simple as possible. That is, TA equal to 1, TB equal to 2, TC equal to 1, and TD equal to 2. So that 1, 2, 1, 2 is repeated. And I see that at the end, that is at the edge of below ozone, that is the below ozone boundary, I see the gap closes and opens at something E called 2.23 energy in units of the hopping integrals. This energy I got from Python numerically. I got it. Now I need to quantify this energy in terms of all these 4 TATB, TC, TD. So how this energy relates to this TATB, TC, TD? This is my question, and this question was arised from the motivation of the research. So when we were doing this problem, there was a paper by Maria Maffis, and what she does is they analyzed SSH4 completely. They analyzed SSH4. This band diagram also looks like my one, and the Hamiltonian was also similar. So they have analyzed the model, but there are some problems in that paper. The analysis was okay. It's not that the analysis is wrong. The analysis is right, but there are some problems. The problems are they focused on gap opening and closing at k equal to 0. Here in this figure 2 of the paper, you can go. I have given the reference, so you can go and look at it, and you will see that they have only considered this k equal to 0 gap opening closing. It closes the gap and opens the gap again. But what about this? What about these gaps? They didn't quantify this. What gap is this, or what point of energy is this? No. The energy around which gap opens at below ozone boundary is neither mentioned nor quantified. And now if we come to the caption of figure 2, you see that the model is in trivial topological phase for DD less than AC. They call this hopping integral as, I call it TATB, TCTD, they call it ABC. So these kind of hoppings, that is why the hoppings are in product form, TATB, TCTD, TBTD, whatever it is, why these hoppings are in product form. This product hopping has a dimension of energy square. It has not a dimension of energy, it has a dimension of energy square. So why is it? This is the question. What is the physics that actually drives this? They got this mathematically. They did some symmetry consideration and found this product hopping mathematically, but I wanted to see what physics really drives this product hopping. So in order to understand, in order to solve these two questions, one is this gaps at below ozone boundary, and another is this product hopping. What I do is I use something called decimation or one-step renormalization. What is renormalization or decimation? It's simple. If I have many number of degrees of freedom of the system, a large number of degrees of freedom of the system, I can eliminate some of the degrees of freedom of the system without compromising the actual underlying physics. There is a famous paper of this Madison and Kadanoff. You can look at it. It's very beautifully written, and it can prove that 1D Ising model will not have finite temperature phase transition, and 2D Ising model, that is the Onsager solution, will have finite temperature phase transition in just a paper. This 2D Ising model requires a chapter to to solve it, consider solution. But this person solves it in a paper without doing very much calculation, just because of renormalization. So this is the power of renormalization. Using this renormalization, what I will do is I will map down this SSH4 into SSH to solve that two questions, and I will show that an SSH is hidden inside SSH4 through which the SSH4 does this topological phase transition. So how to do that? This is the SSH4 chain, TATB, TCTD repeated. I number the atoms as 1, 2, 3, 4, and what I do is I eliminate all the even number of atoms like this. I use discrete Schrodinger equation. I write the discrete Schrodinger equation for site 3, site 2, site 4, and I replace this. Just replace simple algebra. And what I get is a coupling between site 1, 3, 5, 7, 9, this odd number of sites. And then the discrete Schrodinger equation looks like this. So we can, the first question is solved. That is in renormalized space. The topological phase transition is happening in decimated or renormalized space. That's why this product hopping is arising, and it has a dimension of energy square. And not only that, the on-site potentials were 0 as of SSH. Okay, but now in decimated space, the on-site potentials are not 0. It has been uplifted to a value of TB square plus TC square or TS square plus TD square. So if I compare it with the discrete Schrodinger equation in that squared space, something energy squared space, I get effective on-site potentials as TB square plus TC square or TS square plus TD square, and the effective hoppings are TA, TB, and TCTD. Now in SSH, all the on-site potentials were same. That's why inversion symmetry of the problem was intact. Okay. And in order to do that, in order to induce inversion symmetry to the problem, what I claim is TS square plus TD square is equal to TB square plus TC square. So for any kind of hopping, this topological phase transition will not happen. This is a constraint equation. This equation is needed to be satisfied in order to have quantized value of the Zach phase or winding number. So now let's explain the gap opening energy also. That product hopping is already done. So in SSH, gap opened at E equal to epsilon. Epsilon were kept to be 0. That's why the gap opened at E equal to 0. But in renormalized space, SSH4, the on-site potentials are elevated to a value of this. So if I now put that, if you remember that TA was 1 and TB was 2 and TC was 1 and TD was 2, if I just put this value in this equation, what I get is E equal to 2.23606. So this was the energy that my computer returned. It was root 5. Okay, so that energy is quantified like this way. Now let's come to finding the topological phase transition using Wilson loop. I use this Wilson loop approach to calculate the topological phase transition. And I see that the Wilson loop, that is the Wilson loop, the formula is this, that is you need the eigenvectors and you need to do a product using a for loop or a while loop, whatever it is. And then I need to take the imaginary part and log of that Wilson loop. And that Wilson loop gives me quantized Zach phase if and only if TS square plus TD square equal to TB square plus TC square, this equation is satisfied. Or else I don't get the quantized value of Zach phase, and it's quite natural because inversion symmetry of the problem is not. That's it. So these are the two plots of the quantized value of Zach phase. It's exactly quantized to 15th decimal place. It is minus pi and plus pi. And that's why I took all these nasty kind of values, because in order to satisfy that equation, you see, you will check that this will satisfy this equation, and for TATB greater than TCTD, it's in topological non-trivial phase, and TATB less than TCTD, it's in topologically trivial phase. That's why the value of these at these bands, the Zach phase is 0 there. Now let's come to the edge states and the bulk boundary correspondence once again. So the bulk boundary correspondence, in order to do that, the chain should start with a unit cell and end with the unit cell. So I start with BCDA, BCDA, BCDA. It's repeating like that, and then I decimate out all the even number of sites, and I get this chain. And then when I plot the eigenvalues of the system, I think the system is 60. It's the Hamiltonian 60 cross 60, and the system size is of 60 atoms. That is 15 unit cells, because each unit cell contains 4 atoms. I see that in topologically non-trivial phase, where I have Zach phase non-zero, that is winding number 1, I get these edge states are there, and where I have this, the value of Zach phase is 0, I don't get any edge state. Only I get this zero energy edge state in both of the plot, because we don't consider the zero energy anymore, because it's eliminated. E equal to 0 is eliminated from both sides of that discrete Schrodinger equation, because already in Maria Maffei's paper it was done with zero energy, so I don't consider the zero energy once again. And these are the two this plots basically. If I plot the eigenvector corresponding to this eigenvalue, it looks like this, and the zero energy eigenvalue looks like this. This is also a kind of H states. So what are the conclusions of the talk? The conclusions are very simple. From SSH, we know what's topological about topological insulators. It's basically the eigenvectors and the winding number. In SSH4, there is a SSH hidden. Decimation technique helps us to understand gap opening energy, edge state energy, and topological phase transition. We clearly saw that the condition Ts square plus Td square equal to Tb square plus Tc square would be strictly satisfied, and thus topological phase transition for SSH4 is more constrained than normal SSH. So there is a very good physics inside this point. That is, as we go on increasing the generation of SSH, let's say I go from 2 to 4 to 8 to dot 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 something infinity. That is, I now repeat TA, TB, TC, TD, or T1, T2, T3 dot 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 Tn, and the unit cell has gone to till infinity. So what happens is that this condition will be more and more and more and more constrained, and ultimately what will happen is when all hoppings are different, no more phase transitions is seen, and this limit depicts full disorder. Where all the hoppings are different, there is no symmetry of the problem, full disorder, we have no topological phase transition. So my logic also proves this, that as we go on increasing the generation of SSH, it will ultimately lead to full disorder and there will be no topological phase transition. These are my three very simple references. This is a very good book on topological insulators, starting from 1D. Anyone of you can check this out. This is very good. This is my paper, Topological Properties of a Class of Sue-Siver-Hager Variants. It's published in 2021. And this was the paper published in 2028 by M. Maffei and these peoples, which was the motivation of my research. Thank you for your attention.
Thank you so much for this very nice presentation. Now it's time for the question answer session. I can say in the chat box there are a few questions. The first one is from AC sir. Is there any example where the bulk boundary condition is not obeyed? That means, can it happen that we see an edge state but not a topological invariant?
Yeah, this can happen. This is okay. Let me. Yeah, this is seen in this topologically trivial. There are quite good examples of topologically trivial edge state where in topologically trivial state also we can manufacture edge state, and the clear example is this zero energy edge state. This zero energy edge state remains in topologically trivial as well as non-trivial state. So this is a good example of topologically trivial edge state. This can happen.
Yeah, so you mean that trivial means that you are seeing an edge state, but the corresponding.
Yeah, but the corresponding bulk does not have any topological invariant.
Okay. That means
it can happen. But in general, if all the symmetry conditions are maintained, in general,
like time reversal or chiral or something like that.
Yeah, then this should not happen. If we start with a unit cell and end with a unit cell, and if we cut the lattice in very nice way that it should be done, then I think in most of the cases, this condition will be valid. That wherever I will see a non-trivial topological invariant, their edge state will come.
Okay. Got it. Thank you.
The next question is from Shamrat Roy. While you decimate SSH4 to SSH, does each and every properties remain the same, or does it goes like this way that we can do this since each of them are topological invariant things?
Oh, no. When I started decimating out SSH4, I didn't knew anything about topology of this problem. Then I afterwards I calculated the topological invariant. So it's a good question. What I do see, if you see this equation, I don't do any approximation in this equation. These are all exact equations. Okay, I write the equation, and then what I do is I substitute this so that there is an effective coupling between the odd number of atoms. And the only approximation that I do is E is not equal to 0. There was E in denominator, which is cancelled from all these. I didn't show you the steps, that's why you are confused. But there was by E, and by E everywhere, and I have cancelled it. That's why I cannot comment anything about E equal to 0. That is only one approximation that is done. Nothing else. But
Okay.
question is intact. So I don't lose any physics out of it. Okay.
Thank you.
Yeah.
The next one is from Shobhik Chatterjee. Is there any specific reason to take the Wilson loop approach?
Oh, good question. I was expecting this question yesterday. Nice. Okay, so there is no general rule that why I took this Wilson loop approach. I believe that if I solve the integral numerically, then also I should get the same topological invariant. But there is the Wilson loop is used because it's a gauge invariant approach, and we know that gauge invariant quantities are detected in experiments. That's why these Wilson loop approaches are used. That if we don't have, let's say, if there is something called convergence of the problem also, where this product will converge. Okay, so it might not be that it's exactly pi. So but if we are using a gauge invariant approach, this the dark phase that will be seen in experiment will be matched in theory. That's why we use this Wilson method, nothing else.
Shubhajyoti, thank you.
Yeah.
And just another question. I'm just wondering that this quantization condition, right? That Ts square plus Td square equals to Tv square plus Tc square. Is this somewhat related to taking the Wilson loop approach? I think this is invariant, right?
No. This is not invariant. This is related to inversion symmetry of the problem. Okay, I'm telling you. Do one thing. Just okay. Let me show you the SSH Hamiltonian. This is simple. Don't let. Okay. So this was the SSH Hamiltonian. Okay, 2 plus 2 Hamiltonian. Simple. I am telling you the inversion symmetric matrix is sigma 1. That is uh, 0, 1, 1, 0. Okay, that is the inversion symmetric matrix.
Yes.
So if you do that sigma x inverse this Hamiltonian and sigma x, you will get h of minus k. Okay, now just do it. Make this 0 as a and this 0 as b, and you will clearly see that if these two on-site potentials, these are on-site potentials. Okay, on-site potentials are kept to be 0 in SSH, but these on-site potentials are different. Let's say this is a and this is b, or epsilon 1 and epsilon 2, and if you apply that sigma x matrix, I guarantee you that inversion symmetry will not be there. This will be b and this will be a. That's why inversion symmetry will not be there. It will be not be that h of minus k. But if it is a and a, then again inversion symmetry will be restored. And that condition that I showed you, T square plus Td square, this condition basically restores the inversion symmetry of SSH4. That's why it gives quantized value of the Wilson loop as well as dark phase.
Okay. That's great. Thank you, Shubhajyoti.
Yeah.
And very nice talk. Thank you.
Any other questions?
No, I guess there is no more questions here. So thank you so much for this nice presentation. The posters are already uploaded in our Slack channel. I would also request the oral presentation speakers to upload your slides in our Slack channel so that we can continue this discussion further. Now it's time to move on to our next talk. Our next speaker is Mr. Debaprem Bhattacharya from Government College of Engineering and Textile Technology, Berhampur. You can start your presentation now.
Am I audible?
Yes, you are audible.
Give me 10 seconds to share my screen.
Yes, sure.
Is it visible?
Yes, your presentation is visible.
Okay. Many thanks to the organizer of this seminar for allowing me to present my work here. And a very good afternoon to all of you. So today I am going to present here a new low energy two-dimensional carbon semi-metal other than graphene. So we all know about carbon, and carbon is a very versatile element, and it combines with the two carbon atoms combine with each other in many possible ways. So this unique hybridization feature of carbon allows us to have many number of allotropes in all dimensions. Like in 0 dimension we have fullerene, In one dimension, we have carbon nanotube. Two dimension, we have graphene. And in three dimension, we have diamond and graphite, etc. But today we are more interested in talking about two-dimensional things. So graphene here is very much studied for nearly last 2 and 3 decades. So, but there are, of course, graphene is studied for its unique properties and applicability. But there are other two-dimensional forms of carbon which are reported in the literature, mostly in theoretical manner. But that is not all. But there are certain materials which have been proposed long back, have already been synthesized not in commercial way, not in large scale, but in laboratory scale, like graphene, PhD graphene, polygraphene. These are some materials which have been synthesized in laboratory scale, and some nanoribbons of graphene, TPH graphene have also been realized in the laboratory. Now, the question is, how do we look at these allotropes in terms of their formation energy? Here we have plotted a graph showing the formation of energy of quite a large number of two-dimensional carbon allotropes with their carbon density. And here in the graph, these square points represent semi-metallic allotropes, triangular points represent metallic allotropes, circular points represent semiconducting allotropes, and diamond-shaped points represent double Dirac materials. So in this graph, you can see that graphene takes the lowermost position, and that black square with red outline is the position of the graphene, and that has the lowest formation energy. And just above that, there is a cluster of points denoted by that arrow mark. There, certain number of proposed structures fall, like far graphene, SW graphene, pi graphene, and Shi graphene. And the pink spot, the color is not so visible, but the arrow pointing to that square mark is the proposed structure by us. We have named it warm graphene, and that particular structure is a very low energy structure, which has the possibility of synthesizing it maybe in the near future. But the points inside the cluster, one of the points inside the cluster is far graphene. Its nanoribbon has been synthesized successfully in the laboratory. So we are hopeful about synthesizing this two-dimensional carbon material in near future if the chemistry is taken care properly. So having low energy is very important of realizing a structure practically in the laboratory. Now, how does the structure look like? This warm graphene structure contains 20 atoms in orthorhombic unit cell with space group PBMN. Its lattice constants are 11.716 angstrom and 4.586 angstrom. The planar carbon density is 0.372 atoms per angstrom square, whereas that for graphene is 0.377 atoms per angstrom square. This is quite close. Even the formation energy is minus 8.9 electron volt per atom, whereas that for graphene is minus 9.22 electron volt per atom. It has got 6 non-equivalent carbon atoms in its structure, and it's a non-magnetic structure. So even having an orthorhombic cell, it can show semi-metallic behavior. So hexagonal symmetry is not a prerequisite for getting a Dirac cone in the band structure. Whether this structure is stable or not, that is the next question. To this end, we have performed phonon spectra to analyze the dynamic stability of it, and we have found no negative frequency mode in the phonon spectra, and the highest common mode is under 55 terahertz, and which ensures that the structure is dynamically stable. For checking its thermal stability, we have performed a molecular dynamic simulation in canonical ensemble for 6 picoseconds at 1000 Kelvin temperature, and we have seen no drastic change in the average energy of the system, and there is no loss of structural integrity, confirming that the structure is thermally stable at 1000 Kelvin. Even the mechanical stability is also checked by checking the bond one site area of mechanical stability for orthorhombic crystals, and that is C11, C22 minus C12 square should be greater than 0 and C44 should be greater than 0. And these are the values we have obtained from the strain energy curve, and by suitable parabolic fit we have estimated these values to be 353.47 Newton per meter, C11, and C22 is 333.47 Newton per meter, C12 is 72.7 Newton per meter, and C4 is 30.90 Newton per meter, which actually satisfies the relation given here. And in this respect also we have calculated the in-plane Young's modulus and Poisson's ratio of the structure. It shows an angular variation, and that means it's an elastically anisotropic material unlike graphene, and its Young's modulus is in the A and B directions are respectively 317.51 Newton per meter and 337.56 Newton per meter. This value for graphene is close to 345 newtons per meter. And that for Poisson's ratio is 0.26 in A direction and 0.219 in B direction. Now, coming to the band structure of this material, we see that it's a non-magnetic semi-metal, and the bands around the Fermi level is mostly due to the pz orbitals of the atoms, and the Fermi velocity is anisotropic, and the maximum value of Fermi velocity is 6.85 into 10 to the power 5 meter per second. We have also done a tight binding calculation considering only the nearest neighbor hopping, and it seems that the DFT results and the tight binding results match very closely. And the Dirac point here is having a unique feature. We have seen that this Dirac point does not change its position, neither it splits due to the application of strain within a range of 10% compressive to 10% tensile biaxial strain. This is also verified for uniaxial strain within the range of -7% to +7%. That means 7% compressive to 7% tensile strain. So this strain resilient Dirac cone behavior is one of the unique features of this material. We have also checked the defect-induced magnetism in this material. In the 6 non-equivalent sites, we have created monovacancy defect and observed the magnetic moments and the vacancy formation energy. This is shown in the graph. Here we see the C1 site and the C3 site have the maximum and minimum magnetic moment respectively of 1.77 Bohr magneton and 1.01 Bohr magneton respectively. This value for graphene is around 1.5 Bohr magneton per monovacancy. And the highest and lowest formation energy, vacancy formation energy is seen in the C1 and C2 sites, which is 7.38 electron volt and 4.32 electron volt respectively. And this for graphene is of the order of 6.92 electron volt. We have used this material to construct some one-dimensional derivative of it also. Nanotubes are formed with this, with limited number of chiralities, I'll say. Only 20, 02, 30 and 03 chirality have been tested. Because of the lack of computational resource, because studying these nanotubes require a lot of computational resource because of the number of atoms becomes very large for different chiralities. But the interesting feature is we have seen that for 2,0 and 3,0 chirality, the material remains semi-metallic, and for 0,2 it becomes semiconducting, and for 0,3 it becomes metallic. So depending on the rolling direction, nanotubes can be semi-metallic, metallic, or semiconducting even. And the curvature energy is found to decrease with the increase in radius of the tube. We have also studied the optical property of this material, and this optical property of this material is strikingly different from that of graphene. In the electron energy loss spectrum, we have seen two peaks at 1.76 electron volt and 2.72 electron volt. But for graphene, it is close. The peak is around 5 electron volt. That is beyond the visible range. So some optical activity can be seen. Optical response can be seen within the visible range for this material, and near 488 nanometer range, it shows a significant amount of absorption of light and 10% reflectance of light. So its optical behavior is very much different from graphene. So it can be used for some optoelectronic devices. So concluding the findings, we can say that the energy and the atomic density of the system is reasonably close to graphene. One graphene has been found to be thermally, mechanically, and dynamically stable. It is elastically anisotropic unlike graphene, and its constants are comparable to graphene. The origin of the semi-metallic behavior could be explained from simple type-binding Hamiltonian considering only nearest neighbor interaction. The material shows strain-resilient Dirac cone. Monovacancy defect induced magnetism could be useful in developing spin-based electronics at room temperature. Tweaking the material in a technologically suitable way, it can be used as a potential optoelectronic material also. Besides this, mechanical strength. Carbon being a very potential material, very practical material, perhaps the next generation of its research may be heading towards finding new 2D forms of scalable manner which can be valuable for practical application. So in this respect, we have published one paper in this journal, and my co-author was Professor Devnaran Dana of Calcutta University. With this, I want to thank you all. If you have any questions.
Thank you so much for this nice talk. Now it's time for the question answer session. The first question is from our previous speaker, Shubhajyoti B. Are you using DFT for phonon spectra? If yes, which software and what basis set?
Yes, I am using performance spectra. I have calculated this with Quantum Espresso. I have used a combination of Quantum Espresso and Phonocle.
Okay. He has another question. What functionals are you using in DFT band structure calculation?
Yes, in DFT band structure calculation, we have used GGA PBE band, GGA PBE exchange correlation function.
Okay, PBE, isn't it?
Hmm?
PBE, no? Hello?
Audio is not clear. I cannot hear.
PBE functionals are you using that?
Yes, PBE.
Oh,
GGA PBE.
Yeah, GGA functional. Okay. Yeah, I can understand. Thank you.
Okay, the next one is from Shobhik Chatterjee. Is there any relation between shifting of degeneracy with the increase of strain? That means, by what means they are related? Of course, we can see the result in the plots of strain resilient Dirac cone.
Uh, Actually, I don't know what is the relation between the shift of the Dirac point with strain, but the shift is very less, very insignificant shift. I mean, there is not a drastic.
Yes, yes, we have actually observed that, right? That we are changing from -10 to +10, and
Yeah.
the gamma point diversity is very less, and the degeneracy is very close to the gamma point. So I
Yes.
thought there may be some relation between those two quantities.
No, I exactly don't know why it shifts, but it has shifted. I have checked it numerically. There, the point has shifted towards the gamma point, but with a very slight amount.
Okay, okay. Thank you.
There may be some physics behind it, but I actually don't know.
Okay.
The next one
Uh,
is from SSR.
okay, follow me just a moment. I posted the same question twice, so just read the first one, please.
Yes, okay, sir. Will the transient strength of worm graphenes be as good as graphene?
Strength-wise,
No, I mean the tensile strength.
the tensile strength for graphene is elastically homogeneous, but it has elastic inhomogeneity. I mean anisotropy. So in A and B direction, the strengths uh, may be nearly equal, but in other direction, the strengths may not be equal, because I have seen that the in-plane Young's modulus varies by a large amount.
Okay.
But if we have multi-layer of this material with random orientation, we can regain this strength by
Okay.
this number.
But this is yet to be studied, I believe. I mean,
Yes, absolutely. Yet to be studied, and we are hopeful that someday this will be synthesized, and there is a fair probability of the material being synthesized, because nowadays some reports are coming of synthesizing new dimensional material in the laboratory scale. So we are hopeful, and in fact it has got low energy also, so the chances are quite high.
okay. Thank you. Okay, cool. Yeah, done.
There is no more question. So thank you so much for your nice talk. So we are at the end of our first session. Thank you all for listening. Now I would like to hand over the mic to Shobhik.
Yeah, hello, am I audible?
Yes, you are.
Okay. So I would like to thank our oral presenters as well as Paulomi to take the charge of this session. And we are here at the end of our morning session of day 1 ICCMSP. Thank you everyone for staying tuned, for listening to the talks and raising questions. There are really interesting sessions there. So I have posted the session details in the chat box, which are in the second half. So we shall resume at 2:30 p.m. sharp, and the lunch break is beginning just now, and I officially end our morning session hereby. Thank you all for listening.